That sounded such a simple idea. We decided to use Arduinos or similar and have a go at 3 projects. First two are the ground sensing ones, so that's resistivity and magnetometry, and the third one is GPS, because archaeologists need to know where they're measuring and what they're looking at. If you've ever watched Time Team, this is bread and butter stuff. I will try and explain it in the time available. So, if you're doing archaeological surveying, you need a decent GPS. They sort of look like that, start at about 3.5 grand, go up to about 9 grand. But for that, you know where you are to within a centimetre. Resistivity, you've got a unit there, stick 2 poles in the ground, stick it in the ground, wait a second, it beeps, you pick it up, you move along a metre, put it in the ground, it beeps. What you're doing is measuring the resistivity, which gives you a measure of the amount of moisture in the soil, which, if you've got buried rocks, the moisture in that part of soil is different to the soil that's been undisturbed. If you're very lucky and the gods are with you, you can see things. Magnetometry, commercial unit, it's got 1, 2, 3, 4 magnetometers. Quite posh ones, they're iron cord and they're hand wound usually. And there's a company in North Wales, I think it is, that actually makes them at sensible prices. But you walk up and down, and if you're lucky, you'll be able to see things in the ground. And if you've ever watched Time Team, you'll know that you need to be lucky most of the time. And that will show you burning and similar things in the ground. The idea is to reduce the amount of time you spend digging and only dig where there's stuff to find. So we did a resistivity survey at an abbey near where I live, and using open source ordnance survey maps, that gave us the modern ordnance survey map location, using, and that road there is off a 1901 ordnance survey map, geo-referenced, which means that building is the same building in all of the different plans. The yellow bit, sorry, this bit is a 1768 map, which utterly destroyed my head because the orientation of it was east is north. They didn't have standard north then. Sorry, that hurt. And we plonked all those together, and this was our resistivity survey, and we were lucky. Hooray! We found stuff. And you can just see, honest, truthfully, that's where we thought there were some buildings that aren't there now, but the resistivity survey showed some slightly darker blobs, and other members of the same archaeological society actually dug and found stuff. And it worked! We were very lucky. I spoke to one of my colleagues. I work in a university, but I'm on the IT side. I spoke to someone who teaches this stuff, and we worked out that we were working with an average error of about 8 to 10 metres. So to just have everything line up and work, phew! GPS. Quickly, how many people got sat-navs? Use them? Yeah? Right. You use this stuff. Originally put up by the US military for US military purposes. Now everybody uses it. That's what's called a constellation, and that's the original satellites that they launched. There's nearly always, you need 4 to get a decent lock. Actually, you need 8 to get a decent lock. So, why try and build your own? Well, the ones you can buy for £100 or £200 only get you to an accuracy of somewhere between 4 and 10 metres. Originally the spec was 70 metres. That was good enough if you're throwing thermonuclear weapons around. That's what it was designed for. You can buy commercial units, and they range in price from ouch to how many bells and whistles, because that drives exactly how much you're going to spend on the kit. If you want it in real time, I'd stand there, read it, and if you want to read it in an OS set of map references, you just spend some more money. Various accuracies, standalone. The picture I showed you earlier uses a technique called differential GPS, so you have a base station that you sit and you wander around with another unit that communicates back to them. The logic being that what the base station sees as errors are common to your unit, so you can take those errors out and it much improves it. You'll get about 1 to 2 metre accuracy that way. Huge rate of progress. I've seen one market report that said by the end of this decade, our phones will be accurate to under a metre, possibly even 10 centimetres. Such is the rate of progress. So, just as not all Hoovers are made by Hoover, not all GPS systems are made by the Americans. So the jargon is GNSS, Global National Satellite Systems. The Russians have got their own. Europe's has just, I think, launched the 4th satellite last year and is now coming on stream. Chinese, worldwide system, and there may be another one. You read the reports and it's as clear as mud. If you have a unit that talks 3 different satellite systems, that's much better because you're backing off the errors against each other. There is a technique that makes it slightly more accurate called SBAS, and of course it's aerospace and there's engineers in it and they invent jargon faster than anything else I've ever seen. So there's a posh system that they have some more satellites looking at the other satellites, telling you the errors that they're seeing. And the Americans call theirs WAS, the Europeans call it EGNOS, the Japanese have 2 different systems, the Indians have their own system, the Russians have their own system, and there are other commercial systems. If you're a surveyor, you may well buy your kit from Leica or Trimble or a couple of other firms, and they have their own worldwide systems. If you have to ask, you cannot possibly afford it. So how accurate is a GPS? Well, I dug into the original specifications that were published in 2008, and apart from the gobbledygook, you put some numbers in, which I'm very glad they did a worked example for the student. And A is reserved because that's the military stuff. It's encrypted, you can't get at it, and they mean you can't get at it. And B is the normal commercial stuff that you and I use at sat-navs, and you have about 14 metre accuracy 95% of the time, so 5% of the time it's going to go whappy. And vertical is 27.5 metres 95% of the time. So some practical results. Is it possible to dim the lights on this one, please? Sorry, I went for a very dark. I don't know how well it's visible. No, right, okay, sorry. Right, that is the point at which I turned my little Arduino GPS, thank you, combination on. The software simply says, oh, that's 0.0, that's where I know where I am. It was actually sat on the windowsill of the dining room at home. So that's very important. It was not moving. My house does not suddenly shift 15 metres. The GPS is lying. So it did an average of about 26, 27 hour run, and the average that it came back to is there, which is about 6 to 7 metres away from the first guess point. To do this properly, I will have to do root mean square of every point, and I was trying to do that this week in Excel, and I'm sorry, I ran out of time. That was the instant point of the particular reading. Now, your GPS sticks out stuff up to about 4 to 10 lines every second, and you'll see that a bit later. But it wandered off, and hey, it went for a nice little wander there. According to that, my windowsill was moving at 3 knots. No. I don't know why I might have tracks in my house. I don't have. Perhaps that's that's a 10-metre circle, that's a 15-metre circle. And that's a standard plot for a commercial grade GPS. That's latitude, longitude and height. The red line is the average. The green line is the spot reading. And you can see it went mapping. And I have a hunch, but I cannot back this up with any theory or research yet, because I can't read the paper. Well, I can read the papers, I just don't understand them. The physics and maths of space flight and high-level atmospherics is beyond me. But I have a feeling that it's what I would call atmospherics, so that's a combination of ionosphere, whether the satellite's wobbling, whether the clouds are there or not, etc., etc., etc. The people at NASA and MIT are doing a research project in the States to work backwards from GPS data to what it tells you about the weather, because they're interested in flash floods in California. That was the satellites I happened to be seeing at that instant. Like all technical things, there's 2 different ways of numbering the satellites. I won't bother. And these red dots were the satellites I was actually seeing. But the important thing is I was seeing the satellites in that arc. And trust me, I can see it here. I don't know how it comes up at the back. I'm sorry. But you can see the arcs of the satellites as they passed overhead. And there's that bit which no satellites appeared at. Well, I'm reasonably high up here in terms of northness. They don't have polar satellites. This is the satellite that looks at the other satellites, and you can't see any there, but every 10 minutes or so you get a quick little blip, and you'd see one. That's what you actually get out of your GPS unit, and my word, it's mind-numbing, because you have to try and decode it unless you've got software that does that for you. And there are all specifications, and they date back from the days when the primary use of GPS units was to tell ships and boats where they were. They run at 9600, 4800, or whatever you set the baud rate to be, and they're designed for use to talk to other shipboard navigation systems. So there's an awful lot of redundancy. There's a checksum on every line. And this, for example, the first thing it does is say, hey, I've got 4 sentences of data, and this is the first one. I've got 4, this is the second, 4, this is the third, etc. And so your software is going to have to munch those. These are the standard sentences. There's about 6 of them, 5 of them, whatever. If you're trying to do high precision GPSs, you are going to need to understand and design your software to cope with the other 10. Done that one. There's 2 or 3 sorts of chipsets. There's the cheaper one you find in your sat-nav, you buy from Adafruit or whatever. That's unfair to Adafruit, theirs is in the middle one. It does all sorts of additional stuff. Or there's what's called the professional, and this is where it gets very peculiar as a market. The expensive stuff and the cheap stuff sometimes are as good as each other. The devil is working out what you want it for. Hint for anyone thinking of doing this, you will have to use that piece of open source software. There is nothing else, well, there is nothing else available that's as good and cheap. You can pay a lot of money for that. That's proprietary. I would commend you to read that. It understates it, believe me. The documentation, if you're lucky, is best Taiwanese. If you're unlucky, it's poor Taiwanese. That's what we're using. A friend of ours also has some open source mobile phones, which we think has the right chipset to do the fancy stuff. So to answer the question, is geophysics affordable and can you do this at home? The answer is, for GPS, for 500 quid, yes, definitely. Can we do it? Well, if anyone wants to give us a hand, that would help. We're not programmers, we're struggling. Have we done this in our anticipated time? Don't be silly. We thought we'd finished by now. We're about 20 to 30% of the way through the first project. But it's been great. There's some new crowdsourced products come through which do quite high level spec stuff. And found a paper where a university researcher went off and did all this stuff on a beagle bone and published it and had it refereed. He was accurate to 8 centimetres. And that's it. Sorry to rush, it's a topic that you can spend quite a lot of time talking about. Any questions?
So, how far through are you on the resistor and magneto?
Not started at all, but there's some interesting stuff going on that I'm not allowed to talk about in public at the moment. That's all I can say, which will help. Oh, sorry, that's the resistance. Yeah. The magnitude, magnetometry, we know someone who's implemented a system using an Arduino. We know how they've done it. We know where they bought bits from. What we don't know is how sensitive it is.
I'm just interested in those errors from your windowsill. If you had two of the same device sat next to each other on the windowsill, would they think they're always next to each other, or would the errors be random?
I have no idea. The logic says it would be the same, but it would be an interesting proof of concept.
It should be, or differential GPS would work.
Yes, but sorry, I've been in IT and electronics far too long. I don't should and ought are two words that cause me to go, no, you don't know. You haven't measured it.
So the error theoretically at any rate is environmental rather than from the device?
Allegedly, yes.
We've actually done this as part of the CSI Run Once More project. We've done Poor Man's GPS, where you get Google Earth imagery. You go out into the field, you put your handheld GPS on a point that you can recognise from the imagery. You let it settle for 5 minutes. You write down the 10-figure grid reference, and then you use the variation between what you see and where you know it is for half a day, and you can get something like 2 meters accuracy from that repeatedly. It's great. There's about 5 different sources of error in a handheld GPS reading, and of those, there's 4 of them that are going to be coming to any 2 units in the field. Things like the atmospheric scatter is going to be the same for 2 GPSs in the same, literally, field. So there's only one source of error left by all this. I mean, people really slag off, people who haven't used GPS much practically slag off its accuracy. But in practice, if you've got a good view of the sky, which your windowsill with respect is not.
I was using an active antenna.
Okay, but the top of Oakley Moor is basically perfect. No tree cover, view to the horizon all the way around. And the accuracy you can get from that repeatedly is absolutely fantastic.
I also want to point out that our project aim is 25 centimetres, because that's a quarter of a test pit. So
next question over there, please.
Slightly dark question. If the objective is cheap geophysics rather than cheap GPS, have you tried triangulating cheap GPS with other technologies like ultrasonics, you know, sort of like wayfinding cameras used. It struck me that if you're doing something size of the field, if you've got like one reference point and you can do the best possible GPS with that, then if you combine the two, if you just want to do it on an Arduino really cheaply, then in a way you get very high degree of accuracy, wouldn't you?
There is an interesting project paper that I've come across in the last 3 months talking about use of large numbers of cheap GPSs, and there's a picture of the car the guy's used, and there's 8 GPSs at the front and a similar number 4 metres back on a very long piece of wood. And he's driven that, and it's got very high accuracy. Again, it might be because of my lack of programming knowledge that we haven't gone that way. And yes, there are lots of other things you can do.
I'm loving the ultrasonic.
Got another question
side of
over
it.
here, I think. Sorry, don't hold you, because we've only got 10 minutes in each of these sections. Please.
Oh, I think you basically answered it.